Hi Math 215 students. In this video we're going to talk about the matrix of a linear transformation. So if the outcomes for this video are pretty simple, you want to be able to define the standard matrix of a linear transformation, you want to describe the connection between matrix transformations and linear transformations, and write down the standard matrix of a given linear transformation. So let's review a couple of those terms from the outcomes. We talked in the last video about matrix transformations. We said that a matrix transformation is a function that you get just by taking a fixed matrix and multiplying it onto a vector where the vector and the matrix have the sizes that make it work. All right, so AX is a matrix transformation whenever A is a variable and X has as many entries as the columns of A. Now, on the other hand, a linear transformation is any function or mapping that satisfies these two properties. We have sort of the addition property and we have the scalar multiplication property. And if you want more detail, please go back and review the last video for that. Now, we commented in the last video that if T is a matrix transformation, then it already does satisfy both of these properties, and therefore it's automatically a linear transformation. So every matrix transformation is a linear transformation. Now, we promised last time, and we'll fulfill in this video, that we will see that vice versa is true, that every linear transformation can be thought of as a matrix transformation. And that's actually the exact point we're going to say. Our theorem for this video is this: if T is any linear transformation, then there is a unique matrix A that makes T of X equal to A of X, no matter what X is. So, given any linear transformation, even if it's not told to us in terms of a matrix at all, there is some matrix out there that gives us the same result. The question for us now is, how do we find that matrix? Now, we're not going to dive deep into the proof of this, but you're encouraged to read your text and see why that is. And the proof of this will actually proceed by answering the second question: how do we find the matrix of a linear transformation? And here is the answer. The matrix A that makes T of X equal to AX is the matrix whose columns are T of E1, T of E2, and so on through T of En in order. That matrix is called the standard matrix for the linear transformation T. Now, just to remind you, or maybe this is new to you, but it's an important thing to remember, E1 is the vector that has a 1 in the first position and zeros in all of the other positions. E2 has a 1 in the second position and zeros everywhere else. E3, E4, and so on all the way through En, they each have 1, 1, and then zeros everywhere else in the vector. And so what this theorem is saying is that if you want to find out what matrix A makes this theorem work, what you should do is take your rule, whatever it is, apply it to the vector E1, and make it that, whatever it turns out to be, the first column of your matrix. Make the second column of your matrix whatever you get from applying T to E2, and so on all the way through the nth column, which will be T of E sub n. Okay, so we will see a number of examples to emphasize this theorem, but that's the main point of this video. So let's take a look at our first example. In the last video, we decided that this map that takes the vector x1, x2 and sort of scrambles the coordinates together to produce this output vector, we decided that this was a linear transformation. And now that we know that every linear transformation can be written as a matrix transformation, we're going to ask, what is the standard matrix of this linear transformation? Now, you may already kind of see how to arrive at this through matrix multiplication, but even if you don't, we're going to be okay, because we remember that theorem. It says that if T of X equals AX, then the way to find A is to make the columns of A equal to t of 1, 0 and t of 0, 1. That's the vectors e1 and e2, and we'll remember that our domain is R2, so two vectors is all we need. Now if we were to take t of 1, 0 and put it in here with x1 equals 0 and x1 equals 1 and x2 equals 0, we can figure out what that is. And if we were to do the same thing with 0, 1, we can find out the value for each of these columns. The first column should read 3, 1. The second column of A should read -2, 1. And so the standard matrix will be exactly the matrix 3, -2, 1, 1. Now, if you're interested, go ahead and plug in a couple of vectors for x here. Randomly choose x1 and x2 as sort of see what the outputs are, but then do the same thing by multiplying this matrix onto your vector. And what you should find out is that actually they give the same answer. T of x, this rule up top, and A times x are the same thing. Okay, as a second example, in our last video we saw a couple of linear transformations that came from photo editing. And so in the last video we specified what the matrices were, but now we're going to show you how to find out those matrices from what's been given you. Okay, so as we start, we take a look at this linear transformation. And we said back in the last video, it looks like this is flipping everything across the y-axis. So this linear transformation is a flip across the y-axis. And so what we'll do is take that idea that it's reflection, and we'll see what happens to 1, 0 and 0, 1. What happens to the vector 1, 0, remember that's along the x-axis, if you were to flip it across the y-axis? Well, the vector 1, 0 would be flipped across and become -1, 0, while the vector 0, 1, which is a point on the y-axis, if we flip that across the y-axis, nothing changes. It stays 0, 1. And so the matrix we'll get is -1, 0 and 0, 1. Now remember that the 1, 0 had its image, -1, 0. The 0, 1 just got sent to itself. And so these columns of A come from what happens to these specific vectors. And that is the matrix that produces this change, as shown there. Now the second example we looked at with photos in the last video had to do with this one. This one was a scaling. We were making everything bigger. And so if we were to take a look at 1, 0, now the axes are not marked, so let's just say 1 is the coordinate of lying directly underneath the baby's eye. And it measures this much in this picture, but it measures a bit more in this picture. And comparing the length here to the length there, you can see there has been an enlargement. If you were to look very carefully, you might judge that the new size is about 1.5 the old size. And so 1, 0 should be sent to 1.5, 0. Meanwhile, as we do the enlarging 0, 1, which might be where the nose lies, that's going to be also scaled up the same amount. So 0, 1.5 might be the result of scaling on this here. Now, if that's the case, then our standard matrix should look like 1.5, 0 in the first column and 0, 1.5 in the second column. And that actually is the matrix that we had in the last video. Okay, let's take a look at a slightly different example. Here we're going to talk about a linear transformation going from R3 to R4. So our input will be a vector having 3 entries, and our output will be a vector having 4 entries. And it's not shown, but I'll state, and you can trust me, that this is a linear transformation. And because it is a linear transformation, it should have a standard matrix. So what would we do to find that standard matrix? Well, the theorem says that what we want to do is plug in each of the vectors e1, e2, e3 into this rule and record their outputs. And so if we do that, we'll get the vectors 0, 0, 1, 2. You should check that. We'll get the vectors 1, 0, 0, 1, and 0, 1, minus 4, minus 1. Now, these outputs should form the columns of the standard matrix of our linear transformation. And so our standard matrix is as shown here. And it is also always the case that if you were to take a vector in R3 and apply this rule to it, and take that same vector from R3 and times it onto this matrix, you should get the same answer both times. Right, with that, we have defined the standard matrix of a linear transformation. We have described the connection between matrix transformations and linear transformations. Basically, they're the same thing. Every matrix transformation is a linear transformation, and every linear transformation can be written as a matrix transformation. And we have written down the standard matrix of a linear transformation in the last few examples. If you have any questions, please let me know. Otherwise, I'll see you in the next and final video of this section.